this lesson, we're going to look at probability and Venn diagrams. To begin, we're going to talk about probability.
All right, hi everybody. So we're going to start with the material here in the IB program. We're going to start with probability, and specifically we're going to also relate that to Venn diagrams. We got two ideas here that, I mean, they're different, don't get me wrong, they are different, but they're used together so often that we're going to introduce them together here in this context. So we're going to take a look at probability right now. So to start off with, so just some stuff that we want to go through here. A trial. What is a trial? Well, a trial is an action or experiment for which there are a number of different outcomes. Okay, like rolling a die. Okay, there's a number of different outcomes for rolling a die here. Now, the sample space, S, okay, is the set of all possible outcomes. Okay, so when we're talking about rolling a die, then it's really just the numbers 1, 2, 3, 4, 5, 6. Okay, those are the numbers that we're talking about here if it's a D6 there. Okay. Additionally, when we've got that set that we call the sample space in terms of probability, in set theory we might call that the universal set, and we give it the symbol U, capital U here. And the universal set refers to everything that we are possibly concerned about. Okay. Now, could there be things outside that universe? Yep, I just don't care about them. Okay. So I can define, for example, the students in my room here to be the universal set. This is all that matters. That's it. Now, an event, okay, an event is a subset of the sample space, which contains the outcomes for which the event occurs. Now, what we're looking at here then are we're gonna call, when we're talking about probability, we're gonna call a specific subset of events there a success. These are the successful events that I'm looking for. Okay, so probability, okay, the probability of event A is going to be the number of elements or the number of items in that event A and divided by the total number of elements in that sample space. So this is the number of successful events divided by the total number of possible events. Or it's the number of items in set A, okay, that's that event A, divided by the number of items in the universal set, which are basically the same things here. So just to define that notation just a little bit, let's zoom in a bit, okay, with that little NS there. So when you've got NS there, that's the number of outcomes in the sample space, or it's the number of items in that particular set here. So NA is the number of outcomes for event A. So the sample space could also be called the universal set, and so NU is going to be the number of elements in the universal set, and that's going to be the same as NS. Just two different ways of looking at the exact same thing. Now, a couple of other things that we want to take a look at here. And these are things that you very likely already know, and I'm just reminding you of them. Events which include the entire sample space are known as exhaustive events. Okay? So, and if event A and B are exhaustive, then the probability of event A or B is going to equal 1 here. Basically what we're doing here is we're taking this, let's say that this is this rectangle here represents the set of all possible results. This is my sample space. This is my universal set. Basically what we're saying here, trying to get at here is if I split that into 2 bits, and so this part is A, this part is B, and any possible event here is going to either be in A or B, then that's what this means here. This is the probability of A, and that symbol there is going to mean or, B. Okay, so A or B, this is the union of 2 sets. I'm putting them together there. And that's going to be equal to 1. So now you think about it like this. If we're flipping a coin, this might be getting the head, this might be getting the tails on the coin. Okay, probability is 50%, 50%, or 1 out of 2, 1 out of 2, add those together, you get 1. Now, 2 special exhaustive events are A and its complement, okay, which is not A, which is basically what I've just done up there. Now, we got to make sure that you get some of the notation here. When we're talking about not A, okay, so you've got, basically in this case, what I've got here is I've got A, and B in this case is not A. We might use the apostrophe there, or you might sometimes see the little bar on top. And those are representing the negation of A. This is not A. Whoa, wrong way. So then the probability of A or not A is going to be A or not A, and again, that is going to equal 1. So together, A and not A cover the whole sample space. Now, this leads to a really useful relationship, and we call these complements, by the way. Okay, A and not A would be complements of each other because together they add up to the whole set, or 1 here. The probabilities add up to 1. We can figure out the probability of, A by going 1 minus the probability of not A, or vice versa. I can figure out the probability of not A by simply going 1 minus the probability of A. Okay, so there we go. So just some things to consider here. Let's take a look at some examples, because basically going through the words here, a lot of this stuff should be review. The expectation is that you've seen a lot of this stuff before, and we're really just trying to help remind you of it. Let's take a look at some examples. Okay, so let's take a look at an example here. So a penny, a nickel, and a dime are tossed. Our first question here is going to list the sample space, or the universal set. And I'm going to do it as a set here, but I'm going to create a bunch of ordered triplets here, and these are going to refer to the penny, the nickel, and the dime. Okay, so my universal set here, or my sample space, well, I'll write it as a U here. My universal set is going to be the set of the following results here. I could get a head, 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 and it's going to get a little monotonous here in a second. A head, or a tail. A head, a tail, or a head. I could get a tail. I'll do like a head. A tail, a head, or a head. Okay. So what I've done is I've let that tail kind of work its way through there. Or I could get a. Now how do I want to do this one? I want to go head, tail, tail. Okay. I could go tail, head, head, tail, head, tail, or finally tail, tail, tail. Okay, and that's my total set of every possible outcome that could happen here. So that's my sample space, that's my universal set. Okay, now find the probability that a penny is heads, the nickel is heads, and the dime is heads. Okay, well that is the probability here of H, H, H. Okay, head, head, head there. Now, out of my sample space, okay, there's only one event that looks like that. So that's 1 out of a total of 8 possible events that could occur, or 8 possible outcomes, I should say. Okay. Now, down here, find the probability of obtaining 2 heads and a tail. Okay. Well, now in this case here, I can't just write that out the way I wrote that out here, because this could happen in a couple of different ways here. So what I want to say here is I want to write the probability of 2 heads and a tail. Well, let's take a look at our sample space here. 2 heads and a tail. Well, here we go. 2 heads and a tail. 2 heads and a tail. 2 heads and a tail. Uh-oh. I didn't realize I counted that one twice. So I must be missing one up here. Let's take a quick look here. What am I missing here? I've got tails, heads, 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 tails. Tails, heads, heads, tails. So that should have been... Oh, I'm sorry. That should have been tails. I don't even have that thing anymore. That should have been tails, tails, heads. Yeah, tails, tails, heads. Okay, sorry, my mistake. But we fixed that. So out of this, there are only 3 out of the 8 that give me the 2 heads and a tail. So sorry about that mistake up there. Anyway, there you go. Okay, so in this question we read that 2 regular 6-sided dice are thrown and their sum is calculated. The corresponding sample space is shown below in a 2-dimensional grid. This is called a lattice diagram, typically. So what you've got here, you've got the results on the one die and the results on the other die. And the points here, the grid points, the lattice points here, represent specific outcomes. So the first question here says, on the grid above, identify the event obtaining a sum of 6. Okay, well that can happen a few different ways here. Now, if you've got 2 dice, you can't get a sum of 6 if you've got 6 on one of them, right? So it's got to be like a 5 and a 1. So that would work right there, 5 and a 1. Or it could be a 4 and a 2. Could be double 3s, 2 and a 4, or a 1 and a 5. And so those are your possibilities here. The next one here says, find the probability of obtaining a sum of 6. So we're looking for the probability of the sum of 6. Well, I've got 1, 2, 3, 4, 5 events where that happens out of a total of 36 possible. So that's 5 divided by 36 possible outcomes in that sample space. Now, find the probability of not obtaining a sum of 6. Well, okay, I could go through and calculate all of those, count all of those, or I could do this. This is the probability of, and I'll do it this way, of sum of 6, not. And that's going to be 1 minus the probability of the sum of 6. So that's going to be 1 minus 5 over 36. Well, what I need here are common denominators. In this case, the common denominator is going to be 36. So that'll be 36 minus 5, or 31 out of 36. And that's the probability that we don't get a sum of 6. Okay, so this question says, we're going to toss a coin and we're going to spin the spinner here. So we've got the coin and we got the spinner here. This time we're going to use a tree diagram to show the sample space. So here we go. So starting with our first event here, let's maybe do the spinner here first. So we'll go 1, 2, 3. We identify the 3 possible events here. So 1, 2, 3. And then from there, we've got the coin that we flip. And then from there, for each one of these little endpoints of these line segments here, we're going to identify 2 possibilities. And it could be heads or tails. Heads or tails. Heads or tails. And then at the end here, what we've got here are our little branches. So we could have a 1 and a head. We could have a 1 and a tail. It could be a 2 and a head. It could be a 2 and a tail. It could be a 3 and a head. It could be a 3 and a tails. Okay, so that's my sample space. Those are all the possible results that I could get here. So now the question is, find the probability of tossing a head and spinning a 2. So that's the probability of getting a 2 and a head. Well, when you look through our sample space here, there is only one event that looks like that. So there's only one event out of a total of 1, 2, 3, 4, 5, 6. So the probability of getting a 2 and a head is 1 out of 6. Okay, and then down here, find the probability of tossing a head and spinning a 2 or a 3. Okay, so the probability of tossing a head and this is almost like an inside thing here, it's going to be a 2 or 3. So this is really about the probability of getting. So this is the probability of head and 2 or head and 3. So it's these 2 different events here that I'm looking at here. Well, head and 2, that's 1 out of 6. Head and 3, well, that's just this one down here. And that's also only 1 out of 6 here. So this is going to be 1 out of 6 plus 1 out of 6 here. Now, or, you're going to find as we go through questions like this, or is associated with the operation addition. Okay, because it could happen one way or another, because they don't have to happen simultaneously. It's just one or the other here. I can just add those up here. So that's for a total of 2 out of 6, or reduce down to a probability of 1/3. Okay, so for this example, what are we reading here? It says, according to blood records, 4% of Canadians have type AB blood. Based on surveys, it is thought that 10% of the population is left-handed. So assume that there is not a relationship between handedness and blood type, and that seems pretty fair. Use a probability tree to estimate the probability that a randomly selected Canadian does not have type AB blood and is left-handed. Okay, so let's take a quick look at this. So what we've got here, we're going to split this up here, and this will be, let's say, type AB, and this down here will be not AB. So this is going to be 4%, and this right here will be 96%. Now from there, assuming that there's no connection, so it doesn't matter here, so now we're going to have either you're going to be left-handed or you're going to be right-handed. And so we know that there's 10% are going to be left-handed, so it's going to be 0.10 and this will be 0.90. So left-handed, 0.10, right-handed, 0.90. And so now we're going to create the branches of these by multiplying the probabilities together here. So we're going to get 0.04 multiplied by 0.1 And so we're going to get 0.004. Here, we're going to get 0.04 multiplied by 0.9, and we're going to get 0.036. Now, those are pretty small numbers, but remember, we're talking about a small part of the population here. Now we're going to look at a much larger part of the population. So 0.96 multiplied by 0.1, that's going to be 0.096. Again, still pretty small, but here's where we're going to really see it. We're going to 0.96, and we're going to multiply that by 0.9, and so here we get 0.864. Okay? Now, watch what happens when we add these all up. If you go take 0.864 and you add 0.096, and then to that you add 0.036, and then to add to that 0.004, turns out you get 1. So altogether, this accounts for everything in this population. So what is the probability that a randomly selected Canadian does not have type AB blood, so they're going to be down here, and is left-handed? So type AB blood and is left-handed, well, that's this little bit right here. This is what we're looking for. So we're looking at 9.6% of the population is going to fall into that category, so 0.096 right there, okay? So then you might say it like this. So the probability of being, of not having AB blood, and I'm going to show you a symbol here, and we're going to use this, it's probably going to get introduced a little bit later here, but for and, we're going to use this upside down kind of U here. I'll explain that more a little bit later. And left-handed is going to be 0.096. Okay, and there you go. Okay, in this problem, we're going to introduce Venn diagrams. Okay, and you've seen these before. You would have been introduced to these probably back in elementary there, where we have that little rectangle there that represents everything, the whole universe. And then, whoops, we're going to use circles, okay, intersecting circles to represent sets. And where they overlap, that's meant to be the intersection of those two sets. These are going to be the individuals or the objects that have both these properties in common. So if the Venn diagram alongside the illustrated the number of people in a sporting club who play tennis and hockey, determine the number of people. Okay, so here we go. We're just going to interpret this right here. In the club. Okay, well, in the club here, bear in mind here that what I'm seeing here are actually 4 different sets. Okay, first of all, I've got this group outside here. Okay, these are people that aren't in the tennis group and they're not in the hockey group as well. They're outside that. So that's one group. That's 7. Okay. Then I've got this group right here. This is this little kind of cookie shape here. You ignore all this here. This part right here has got 15 people in it. That's the part that is just tennis. The part inside here, that's the overlap between the two of them, that is both in the tennis circle and in the hockey circle. So what that is that's people who do both tennis and hockey. And then this kind of cookie piece over here with a bite out of it, 26, that's the people that just do hockey. So what we're going to do is we're going to add those all together. And so that will be 7. Okay, wow. I meant to say 15, okay, plus 27, plus 26, plus 7. That's going to be 75. So there's 75 people in the club total. Now, how many people played neither sport? Well, that's 7. Okay, that's the group of people that are outside both of those two sets there. Who play hockey? Okay, now hockey is this circle. It includes this set that do just hockey and this set right here that do both hockey and tennis, but everybody in that circle plays hockey. So you have to add those together. And when you add the 27 plus the 26 together, you're going to get 53. I mean, just think of it like this. If you were to go into that to a room of all these people and say, okay, if you play hockey, stand up. Well, people that play just hockey are going to stand up. People that play tennis and hockey are going to stand up. We're going to get 53 people standing up. How many play at least one sport? Well, the easiest way to do that is just to get rid of that group of people that don't play any of those sports, or either of those sports, I should say. So we're just going to subtract that 7 from our total. And 75 minus the 7, that's going to leave us with 68. Okay, 68 people here that do at least one of those sports. And how many people play both? And that's the whole point of that overlap portion right there. That's the 27 who do both of those sports. Okay, so let's talk a little bit more about Venn diagrams. If you hadn't really seen them before, you didn't remember them, that previous question might have been a little bit more challenging than it was kind of intended to be. So we'll kind of throw that out there. Now let's back up and make sure that we understand what's going on. So a Venn diagram it usually consists of a rectangle, and that rectangle represents the sample space if we're talking about probability, or the universal set, okay, typically. And any circle within it represents a particular set of events or a subset of the universal set. So it's a group of objects inside the universe, but they're all kind of bonded together by a shared property, a shared characteristic that is unambiguous. Okay, so when I put set A in here, it should be very clear whether something belongs to the set or doesn't. Okay, that's one of the defining features of a set, is that the membership is very, very clear. Okay, so Venn diagrams are really useful for solving certain types of probability questions, which is why we're putting these together here. Okay, a number of probability laws can also be established using Venn diagrams, or at least it's really easy to illustrate them. So this Venn diagram shows that the event A, and when we talk about sets, you're going to notice, well, let's do this. When we talk about sets, notice we use these kind of brackets here, these braces. Whatever shows up inside belongs to that set. Now, order doesn't matter. Okay, I could have put this 2, 1, it makes no difference. What matters is whether or not the object is inside the braces or not when we define that set. Okay, so the event here 1, 2, when rolling a die, the sample space S is equal to the set of 1, 2, 3, 4, 5, 6. So rolling a die, that's our sample space. That would also be called the universal set U here, if we're talking about it in terms of set theory. And then we've got this smaller set A, which is going to be 1, 2. And that's what we're seeing over here in this diagram. Whoops. Now, a set. I've just mentioned this here, but a set is a collection of objects for which the rules of membership are clearly defined. And we use them a lot in probability. So here we go again. The universal set is the whole thing, also represents the sample space. Set A, okay, is going to be represented by a circle. Everything inside that circle shares a certain characteristic that we call A, or we're going to represent with the letter A. A primed, okay, is the complement of set A, or we might use A bar on top, right? That is what happens outside of A. So set A plus A primed, or A bar, is going to equal the universal set. Or, another way of thinking about it is the probability of A plus the probability of not A is going to equal 1. Okay? And then we give you an example here where we give you a bunch of numbers in the universal set. 2, 4, 6 is in set A, so that means not A is going to be everything here that's not in A. So that would be 1, 3, 5, 7. Now, let's get into some of the notation here. This little thing right here, that use of that symbol there, that Greek letter epsilon here, that means ownership, so, or it belongs to. So X here, when we read this, X is in A, or X is an element of A, is another way of saying it. Because all the little objects that show up inside a set, we call them elements of those sets, okay? So X here is an element of the set. That's all that means. X belongs to A. So the members of the set are called elements, okay, just to reiterate that. Now, one of the things that we established here, is that when we use capital letters, we're typically referring to sets. When we use the lowercase letter, we're usually referring to an element within that set. So you would normally write like little a is an element of capital A. This notation right here, and I know I'm zooming in and out, but I want to make sure that you see all this stuff. NA, okay, where A is in parentheses, is going to be read as the number of elements in set A. So it's going to give us the size, okay? So the number of elements in set A plus the number of elements that aren't in A, in not A, altogether that's going to equal the size of the universe we're working with. Now, little thing here that has to occur, the zero with the line through it actually has a very specific meaning. It's used to represent what we call the empty set, or what you might see some people refer to it as it's the null set. Okay, so it's the set of objects that has nothing in it. Now it hasn't got a zero in it. Having a 0 in it would be a set with a 0 in it. It's a set that's got nothing in it. So another way that we might write it is this. A set of braces with nothing in between. Okay, so this is the set where if you were to ask, well, how many objects are in the set, the answer is 0. Now, it's not that it's not that it has a 0 in it, because that would be a set with a 0 in it. There is nothing in the set. Okay, there's a few more things we need to say about this. And I've already started to hint at this. I kind of threw a couple of these things down in some of the previous problems here, but here we go. A, U, B. Okay? I'll just make it big here. A, U, B. This is the union symbol. It's a kind of it's a U that doesn't have the line coming down there. It's like like a horseshoe, okay? It represents the union between two sets, which is a set, like this set right here. A union B is a set all on its own. And what it is it's the set of objects that are in either A or B or both A and B. So when you talk about A union B, I'm talking about all three of the sets that are shaded blue here. Now remember, when I'm saying that, I'm referring to the set of items that it's just A, the set of items that are both A and B, and then the set of items that are just B. There are three sets here. A union B refers to all three of those together. Now, here, the upside down union symbol means intersection, A intersection B. And that refers to the set of objects that is A and B together simultaneously. And so that refers to just this little bit that's in the overlap between those two sets. Okay, so when we talk about A intersection B, we're talking about the objects that share characteristics from both of those. Now, a little bit more vocabulary here. Disjoint sets. Disjoint sets have nothing in common. They do not have any elements in common. There is no overlap between them. Okay, so A intersection B ends up being the null set. There is nothing in the set A intersection B when A and B look like this in the universal set, when there's no overlap between them. Okay, so you might think of it like this. It's the set of apples and the set of bananas. Like, here's the set of fruit. Apples here, bananas here. There are no apple bananas or banana apples, okay? There's no overlap between the two of those. Now, it is not possible to represent independent events on a Venn diagram. Now, we haven't really talked about independent events here, but so this is just an idea that we're going to throw out there. We're going to come back around to this idea of independent versus dependent events. Okay, so just kind of throwing this out here right now. So in a class context, we would have a little bit of a discussion about this, and I tell people that just keep that in mind here, that as we're talking about Venn diagrams are really, really useful, but there's something coming up here that it's not going to be super useful for. And I want you to be looking for that when we get there. Now, this symbol, if you kind of take that union symbol sort of and drop it on its side, when we've got A and B related like this, what we mean here is A is a subset of B. And what that means is all of the elements of A are inside of B. Okay, so it looks like this. A is just a smaller set inside B. Now, this usually creates some questions. People ask, can A and B be the same size and whatnot? And the answer is actually yeah, they can be. Okay. But that's just, I want you to think about it right now as looking like this, where A is this set that's entirely enclosed by B. That's what we mean by that. Now, just a little note here. The empty set is considered to be a subset of every set. Okay? So the the null set here is always considered to be, oh shoot, that's not what I meant to say. That is not what I meant to say here. And I don't have the little eraser. Give me 2 seconds here. Maybe I just got it with an easy access, and I do. Okay, it's not what I meant. I meant to just do this. Okay, the empty set is always a subset of every set. Okay, now with a little bit more information, let's go on and do some more questions. Okay, so in this question, we're taking a look at Venn diagrams again. The Venn diagram alongside illustrates the number of students in a particular class that's supposed to stay study, chemistry, and history. Determine the number of students in the class. Okay, well that's just a matter of adding up the number of people that we see in each of the sets. Now remember, once again, and I know I said it a little while ago here, but there are 4 distinct sets being shown here. There's this set outside, and I know that there's 3 people there. Then there's this cookie with a bite out of it shape here. That's got 5 people in it. That piece right there in between, it's got 17 people, and this one over here, this again larger cookie here with a bite out of it, it's got 4. So altogether here, 17 and 3 is 20 and 9. So there's 29 people in the class. Now, how many people study both subjects? Well, it's just a matter of identifying which set we're talking about here, and that's the one in the middle. So that's going to be 17. Who study at least one of the subjects? Well, here we have just one subject being studied. That's the students doing just chemistry. Here, these are the ones doing just history, and these are the ones doing both. So when we add those together, we get 26. Okay? Now, who study only chemistry? Well, that's this bit right here. Okay, that's not this set. Now remember, these 2 sets together, okay, those 2 sets together give me chemistry. So I've got 2 different subsets of this, and we put those together and we get chemistry. But that's the set there that's only chemistry. So it's going to be just 5. And that's how you work that one through. Okay, here's another question, kind of the same thing. In a survey at an alpine resort, people were asked whether they liked skiing or snowboarding. Use the Venn diagram to determine the number of people, here we go, in the survey. Once again, we're dealing with a group of, we're dealing with 4 different sets here. So what we just got to do here to figure out the number of people in the survey, we just have to add together the number of people in the 4 different sets here. So that's 37 that are in just the skiing. There's 9 that are doing both. There's 15 that are in just the snowboarding. And then we've got the 4 over here who are just hanging out at the resort, right? Just having a good time. And when you add those 4 together, we're going to get 65. Now, how many liked both activities? Well, in that case here, who like both activities, we're thinking that they like them both simultaneously. So that's going to be that little section right there, 9. Because remember, we're going to assume that this means that there are 37 people here who like skiing, but they have likely said that they like skiing, but they don't like snowboarding. And then over here would be the same thing here. These guys here would like boarding, but they won't like skiing. So the people who like both are going to be the overlap of the 2. How many liked neither activity? Well, that's going to be this group out here, right? They're the ones that are just sitting at the chalet, enjoying the food and drink and watching people ski. And who liked exactly one of the activities? Well, these guys up here, they're the ones that liked just the snowboarding, and the ones down, skiing, my mistake. These ones down here are the ones that just like the snowboarding. And when you add 37 and 15 together, you're going to get 52. So 52 people like exactly one of them. Okay, so this question here, we're actually going to see kind of the merge of the Venn diagram and probability here. So in a class of 30 students, 19 study physics, 17 study chemistry, and 15 study both. Okay, so we want to put this information on the Venn diagram, and then we're going to determine the probability that a randomly selected class member is something. Okay, so first of all, we're going to fill in the Venn diagram in here. And bear in mind, once again, that there are 4 sets here. We're seeing clearly. Physics is composed of 2 subsets. Chemistry is composed of 2 subsets here. So what I got to do is figure out what the pieces are. So all I know is that 19 people study physics, but that's not enough for me to differentiate or break that up into its 2 different subsets. Same thing here. Knowing that there are 17 people in chemistry, that's still not enough for me to know how to split that up into those 2 different minor subsets there. But I know that 15 study both. So that is this particular subset right here. Because that is a piece of the physics set, if there's 15 here and there's supposed to be 19 total, I know that there are 4 here. Same thing with chemistry. If there's supposed to be 17 here and there's 15 here, then I know that there must be 2 right there. Now, I also know that in this particular class, in this universe, if you will, there are 30 people. And so normally what I would do is I might put a little box over here and just put a 30 there, just to indicate that there are 30 people inside this complete set here. Now, 30 people, if you subtract the 4 and the 15 and the 2, that's going to leave you with 9 people that are outside of both of those sets. So now, what is the probability that a randomly selected person studies both subjects? Well, to study both subjects, okay, you have to be in that middle set there, that subset of both of those. And then we know that there's 15 people there. So that's going to be 15 people out of, because remember how probability works, 15 out of 30. And that can be simplified down to 1/2, okay? The probability of studying both subjects, or the probability of choosing somebody in this class that studies both subjects is 1/2. Okay, how about at least one subject? Well, okay, to study at least one subject, what we got to do is find out the number of people, or determine the sets that satisfy that. Well, that's going to be set A, set B, and set C. Set A and C, okay, are the people that study just one subject, and B studies both. So at least one is going to be the sum of all of those. So 4 and 2 is 6, and 15 is going to be 21. So it's going to be 21 out of 30, because remember, this is probability. And I can divide both of those by 3 to get 7 out of 10. Okay, so the probability of picking somebody that studies at least one of those subjects is 7/10. How about chemistry but not physics? That's right. Wow, can't believe I read that way. Physics but not chemistry. So what I'm asking for here is I'm asking for the probability that someone here is in the physics set, but not in the part of that physics set that overlaps with chemistry. So I want to know that. Okay. So there's 4 people there. 4. Okay. Out of 30. So the probability of reaching in and grabbing somebody who studies physics but not chemistry is 4 out of 30. Now, how about exactly one of those subjects? Well, we were just talking about this a moment ago. When it comes to that, remember, that's going to be this 4 and this 2, because the B there refers to both subjects being studied here. So that's going to be 6 out of 30, or 1/5. Neither subject, well, we bumped into that number almost immediately when we were filling in the Venn diagram. That's 9 out of 30, and we can divide both of those by 3 to get that down to 3/10. And now finally, here's an interesting question. What is the probability that somebody studies chemistry if it is known that the student studies physics? Okay, what's the probability that this person studies chemistry if we know that this person studies physics? Well, this whole if we know that that person studies physics, what that does is that narrows your focus here. I'm no longer talking about the whole class. All I'm talking about is this set of people that studies physics. Okay, I already know that this person studies physics, so that narrows it down to this group of 15 people. Sorry, 19 people. So what's the probability that someone here in this set of 19 people studies chemistry? Well, how many people in here study chemistry? Well, that's the piece that overlaps with chemistry. That's 15. So that is going to be 15 out of 19. Okay, this is called conditional probability. And we're going to explore this a whole lot more in a little bit here. But again, what this is about here is narrowing your focus to a specific subset and then coming up with a probability in that subset, not the whole universe. Okay, so here's another problem. It's going to be very similar to the one that we just did here. It says 50 married men were asked whether they gave their wife flowers or chocolates for their last birthday. The results were 31 gave chocolates, 12 gave flowers, and 5 gave both chocolates and flowers. Now, if one of the married men was chosen at random, determine the probability that he gave his wife. Okay, and we've got 4 questions here. That's awesome, But I need a little bit of help here splitting this thing up here. So what we're going to do here is we're going to create a Venn diagram to help us out with this. And we are talking about a group of 50 men. So I'm going to put the size of my universe out there as 50. And what I've got here is I'm going to have my, what have I got here? I've got flowers or chocolate. So I've got my flowers and I've got my chocolate set there. Now, once again, because there are just the two sets, that breaks up the universe into 4 smaller subsets. And I keep going back to that because I want to make sure that you're getting that. One of the most common mistakes made with Venn diagrams is forgetting how these things split up into subsets and treating the whole thing. Basically, what a lot of people do is they treat all of flowers as if it's just flowers. Okay, very, very common mistake here. So 31 gave chocolates. Okay, but remember, chocolates has got 2 subsets, so I don't know what that means. 12 gave flowers. Not helpful. I don't know what that means. 5 gave both. That's super helpful because that tells me they're right there. And if 5 gave both, that means if 31 gave chocolates, this has got to be 26 gave just chocolates. And if 12 gave flowers, that means 7 gave just flowers. Now, if you put that together here, what happens here is that accounts for 38 people here, which means there must be 12 that didn't do either flowers or chocolates for their wives. So now let's come up with our probabilities. What's the probability that somebody gave chocolates or flowers? Well, if I say chocolates or flowers, remember how or works, right? And we might even write it like this. That's going to be the probability of chocolate or flowers. That's going to be the union of those 2 sets, which means the individual pieces and the overlap together. And if you go 7 plus 5 plus 26 here, that is going to be, there's 38 out of the total 50 here. And if you divide that by 2, what are we going to get here? 19 over 25. So there's the probability that somebody gave chocolate or flowers. Okay, and remember, that's not just one or the other. That could include both. How about chocolates? Probability of getting chocolate, but not flowers. Okay, so chocolate here, but not flowers. So that is going to be, and I know this is a little bit of a weird way to write it, but I'm going to start to kind of push you in this direction here. I want the person who gets chocolates and not flowers. So I know that's kind of weird here, but remember that and there, that intersection means where they overlap here. So not flowers, if I cover up cover up flowers, everything else here is not flowers. And so I've got the 2 sets here, chocolate and not flowers, nothing and not flowers. So what I want here is the chocolate, not flowers. That's going to be 26 out of the total of 50, and then 13 out of 25 when I simplify that. Over here, what's the probability that somebody gave neither chocolates nor flowers? Okay, so gave none of those. So this is the probability of, well, it could have been chocolates or flowers, but this person said, nope, not doing that. So that's nothing in those 2 sets right there. So it's just going to be the 12 that sits outside out of 50. So it's going to be 6 out of 25. And then last one down here. What's the probability that someone give flowers if it is known that he did not give her chocolates? So what is the probability that someone gave flowers? Now I'm going to show you a little bit of notation. And again, this is something that we're going to explore a little bit later on here. All I'm trying to do here is just slowly kind of introduce this to you here. So flowers, if it is known that. So I'm going to draw a line, a vertical line straight up and down here. That he did not give her chocolates. So chocolates, not. So what this means here, what is the probability of the flowers, and this is given that, assuming that there were no chocolates. So no chocolates is going to be everything outside of chocolates here. So that leaves us with only 19 people total to deal with here. This 7 right here is in the flower set. This 12 is outside of both here. So if I want to know the probability of giving flowers, it's got to be inside there. So it's got to be 7 out of the total of 19 people that exist in this not chocolate set. So 7 out of 19. Okay, so here's the obvious next step in this little process here. So 35 grade 11 students were surveyed regarding what technology they have in their bedroom at home. So here we go. We've got 21 students have a phone. So we're going to have a set that has a phone. 16 have a television. 10 students have a computer. So now we've got 3 different sets here. Okay? 8 have a phone and a television. So 8 are in the overlap of those 2. 5 have a phone and a computer. That's the overlap of those 2 sets. And 7 have the overlap of television and computer there. And then 3 are the overlap of all 3 of those sets here. So here we go. So what we're going to do is we're going to illustrate all of this information here in this Venn diagram. And bear in mind that we are talking about the universe here is 35 grade 11 students. So here's phone, computer, and TV. Now, when you've got 3 sets in here, okay, 3 kind of these distinct sets here, that breaks up the entire universe into 1, 2, 3, 4, 5, 6, 7, 8 smaller subsets. What I need to do is I need to figure out what the numbers are that belong into each one of these smaller subsets here. Now, right now, I'm not given information like that. I'm given, for example, that there's 21 students have a phone. Well, for phone is broken up into 4 subsets. Okay, ignore all the rest of that there. Phone all by itself has got 4 pieces to it. So does computer, so does telephone. And if I talk about, for example, I have 8 students here have a phone and a television. Well, phone and television, ignore everything else here, that's this little bit right here. That's these 2 subsets together. That's still not enough information for me to differentiate. Until I get told this, 3 students have all 3. Well, this is the all 3. This is the subset that intersects with all 3 of those. So this is where the 3 goes. And as soon as I have that, well, the rest of this kind of falls into place here, because now I can go back up to here to specifically the ones where there's overlap of just 2. So for example, I know that 8 students have a phone and a television. Okay, phone and television. So this piece right here, these 2 sets are the overlap of those 2. So if 3 are in the part of that set that includes computers, there's got to be 5 over here that don't have the access to the computer there. Okay, so here's my 8 in phone and television. Up here, I've got 5 students that have a phone and a computer. Okay, 5 students are in the phone and computer set. This is broken up into 2 subsets. I've got 3 here that also have the telephone, which means there must be 2 here that don't have the telephone, just the phone and the computer. Sorry, don't have the TV, not a telephone. Don't have the television there. They've got just the phone and the computer here. And then finally, we were told that 7 students have a television. I keep doing that. Television and a computer here. So they're in this subset right here. 3 of them are taken into account because they have access to the phone. So that means there's got to be 4 left over that have the television and the computer. Now, I've got enough information here. I can go back up to my original sets here. 21, okay, have a phone. Well, phone is broken up into 4 subsets, and I already have information about 3 of them. So 21 are in the phone subset here, but I've got 5, 10, I got 10 of them there, which leaves me with 11 out here that have just the phone. 16 have a television. That's this set right here, and I already have 3 of the 4 subsets there. So putting that together, there's 9 and 3, that's 12. There's supposed to be 16. That leaves us with 4 that have just the television. And finally, with the computer, we're told that 10 students have computers in their room. So again, out of the 4 subsets here, I've got 3 of them. There's 9. Okay, 5 here and 4 is 9, and there's 1 left over that has just a computer in his room. Now, there's supposed to be 35 people total in this universe here. Let's see how many people I've just taken into account here. I've got 3 plus 2 plus 1 plus 5 plus 3 plus 4 plus 4. Well, that's 30 people total taken into account by these three subsets, or sorry, these three sets here, which means there's got to be 5 left over that sit outside of those three sets. And now we filled in all the bits of information that we need. Now we can answer the following questions. What is the probability that a student chosen at random has a phone or a television? So that is the probability of phone or television. So we already know that there's going to be 35 people in this universe, so that's the denominator. But with phone or television, okay, that is the union of these two sets. Now what I could do is I could add up all of those numbers there. But it's probably easier for me to go to 35 here and simply subtract the 6 people that aren't in that set. That means there's going to be 29 right here. So the probability of having the phone or the television is going to be 29 out of 35. And finally here, what is the probability that a student chosen at random has a phone and a computer, but not a television? Okay, so in this case here, the word is and. Up here, this was or, that meant union. Here, this is and. So I'm talking about the overlap between the phone and the computer, but not the television. Okay, so overlap between the phone and the computer are these two subsets right here, but not the television. So I'm looking at just these two sets here, but not the television. Well, that leaves me with just 2 people. Okay, and so what this is going to look like as well here, this is going to be the overlap. This is going to be phone and computer and not the television. Okay, so it's the union of those, it's the intersection, I should say, of those two sets. So it's again, it's these two subsets right here, the 2 and the 3, and not the T. So remember, if I cover up T here, everything else outside that is not T. So where does this overlap intersect with all of this? And that's right there at the 2. And I know for some people that's going to be a little bit hard to kind of get your head wrapped around how that works and how this notation works here. But we're going to continue to practice this, so don't worry too much about it. Just, again, try to stay kind of open-minded about this and, yeah, try to follow along as closely as you can. I'll try really hard to make sure that I explain that as clearly as I can.